Hi, welcome to Learning Monkey. I am Raghu here. In this class, we will discuss about how to check for the given binary tree is BST or not. The explanation is completely based on the assumption that you already have some basic coding knowledge. If you are not good at basic coding, please visit our website learningmonkey.in, take the course placement training for service-based companies, then come for the competitive coding. Coming to today's example, given a binary tree with no duplicate keys, all the keys are distinct keys will be provided. Our task is to check the given binary tree is BST or not, binary search tree or not. And they have given the condition for BST. Left side should have the smaller element and right side should have the large element. So coming to example, this is the input they are going to provide, means they are going to provide you the root node, address of the root node. So 2, the 0 is less than, left side we are having small element, on the right side we are having large element. This is a binary search tree. So output is 1. Coming to the next example, 8, 6. 6 is less than 8, so left side it is small. 4 is less than 6, it is small. 7 is less than 6, 7 is greater than 6. So left side it is maintaining binary search tree. Similarly right side, 14 is greater than 8, it is okay. 10 is less than 14, it is not maintaining binary search tree condition. So we need to output as 0. So this is what we need to output whenever we listen to this concept. The first condition that comes into our mind is so when we discussed the basic data structures, there we have written the coding for searching an element in the binary search tree, inserting an element and deleting an element from the binary search tree. These logics we already discussed in our basic courses in data structures. Once this is the first coding on the trees concept, that's why we want to refresh the concept of the code the way we have written there using recursive functions in binary search tree concept in data structure. See, this is how we have written. Let's understand the logic. So f of root, we have written a function f. The root node is sent as input to that function, and this function is going to call left side node and right side node. Recursively it is calling the functions. So the left side node is called in this function, root tends to left. The next right side node is called in this function, root tends to right. If root not equal to none, this calling should be happened. This is how we write the recursive function calls when we discussed the data structures. So the condition that comes in our mind is whenever we are, the first time in the first function we are calling the root node, from there we are calling the left node and right node, from the left node again call the left and right node. This goes on until you find none. So the point we get in our mind is whenever you are at this position, the first time when you call this function, when the function called the first node, the address of the first node, we think that if you check the condition, left side should have the minimum element less than 8 and right side you should have the element that is greater than 8. If you check that condition, if this condition satisfies for all the nodes, then we say it as binary search tree. See, we have written a condition. Now we have to write a condition here. Left side node contains an element that is less than the data present in the present node. Similarly, right side node contains the data that is greater than the data present in the present node. If this condition satisfied for all the functions, all the nodes, we think that it is enough to check for the BST condition. But this is not enough. Why it is not enough? Let's try to understand graphically why it is not enough. See, 8, 4 is less than 8. It is satisfying the condition. 11 is greater than 8. So the function that called this node satisfies the condition, left side less, right side greater. Similarly, it is going to call this function, call the left node. So 2 is less than 4. Yes. And 6 is greater than 4. It is satisfying the condition. This function again calls this left side function and right side function, because these nodes don't have the child nodes, so it is going to find left side none and right side none. It is accepted. Similarly, right side, it is left 11, 1 less than 11, it satisfies. 22 greater than 11, it is satisfying. But this is not a binary search tree. Why it is not binary search tree? Understand it. 8, when you check the condition here, 8, the elements that present in this entire right subtree, the element should contain in the right subtree should be always greater than 8. But what's this element? 1, which is less than 8. We are missing that condition. We have to check that condition. Whenever you check 1 is less than 11, we accept that. But the entire set of this right subtree, this is what right subtree is. Right subtree for 8. This entire right subtree should contain elements greater than 8. It should not contain elements less than 8. If it is there, we cannot call it as a binary search tree. How to maintain that condition? How to check that entire right subtree contains elements that are greater than 8 or not? How we do that? If you keep track of the minimum element and maximum element, we can identify that. How we do that? Let's try to understand the logic. Initially, we will take a minimum element and maximum element. So initially the function called like this: root node, min element, max element. First time when we call the function, we are going to call min value as minus infinity, max value as plus infinity. But coming to the coding part, we don't have minus infinity and plus infinity. We are going to take negative large number, positive large number, some large number we are going to take. See, each time when you call the function, this function is going to call left side and right side node. Whenever you call the function, you keeps on maintaining the minimum element and maximum element. How you keep track of that? Understand the logic. See, 8. What it means, whenever you call this node, whenever the function call this first node, root node, what is the minimum element that can present in this node? Minus infinity to plus infinity. Any number you can have in this node. But whenever you call the left subtree, from this function we are going to call this node. Whenever we call this node 8, this side should have lesser elements than 8. So you can have up to 7. So that's why whenever this function is going to call the left side function that calling the left node, what is the minimum element? Minus infinity. What is the maximum element? 7. We are maintaining. So this node should contain element between minus infinity to 7. If the element is greater than 7, don't accept it. That is how we are keeping track of the previous values. We are keeping track of the previous values. See, how we got this 7? What's the value here? 8. Less than 1, that is the maximum value here. Similarly, whenever this function called the next node, right side node, the function that is calling the right side node, what is the minimum element? 9. What is the maximum element? Plus infinity. Each time when we call the function, we are going to keep track of the minimum element and maximum element that can present in this node. With that, we are going to maintain the condition of a entire subtree should contain elements between 9 and infinity. We should not get values less than 9. Here we are having 1. It is not accepted. This function is going to call the left side and right side again. So what's the minimum element accepted here? 13. Less than 13. This side should contain elements that are between 9 and 12. Less than 13 means 12. 9 and 12. That is how we call the functions using min and max values. So the element that present here should contain a value between 9 and 12. Only those elements should be accepted. Otherwise, reject it. If that condition satisfies all the nodes satisfies that conditions, then we can say it as a binary search tree. This is the logic we are going to use. We need to keep track of what is the maximum value that accepted this right subtree. What is the minimum value that accepted on the left subtree? We are keeping on track of that minimum and maximum values. Hope you understand this logic. Based on this logic, you try to write the code on your own, then check for the solution. We are going to provide you the code here, and the code is available in our website learningmonkey.in. You can copy the code and you can use the code, you can execute it, but our suggestion is try to solve it on your own, then check for the solution. See, this is the maximum value and minimum value we have considered. It's according to your language, you can choose the maximum and minimum values. So coming to the BST condition, this is the node here. And one more thing, we have just mentioned the static way. Static way we provided the binary tree. You can write the code for dynamic approach, whatever the binary tree you want to consider. So statically we have taken one binary tree and we have sent it to the input to this function, is BST function. You can make it dynamic because these basics dynamically creating a binary tree, that's those basics covered in our basic courses in data structures. Hope you understand these examples. If you have any questions regarding the concept, please post your questions in the comment section below. Thanks for watching. If you haven't subscribed to our channel, please subscribe to our channel and press bell icon for the latest updates. Thank you.